Hello everyone, welcome to this session on Istio and Quarkus. It's a great pleasure to be talking here to you on Open Source Lisbon 2020. In a bit of a different circumstances than usual, it's true. So I hope that everyone's keeping safe and let's have some fun with discovering new technologies, okay? So today I want to talk how we can leverage the resiliency provided by orchestrators like Kubernetes and also the security provided by technologies like Istio and the speed provided by Quarkus, let's say, okay? Essentially, if we look at let's say, the legacy enterprise Java stack, what we really had were big applications that took a lot of memory to run. They took tens of seconds to start, and essentially it was difficult to manage, and the applications became really heavy, right? So in more modern times, with the appearance of microservice, with the appearance of Kubernetes, we are now having services written in Java that are a lot lighter, in around, let's say, hundreds of megabytes of RAM and a few seconds to start. But in essence, this middle layer never really changed, right? We're still running our JVM, we still have our application server, we still have our frameworks, and all of this make the application a bit, let's say, sluggish, okay? So, and this is really a concern when we think about platforms like Kubernetes, okay, where we have different nodes and we want to run our applications. So essentially, the density of those deployments and the amount of pods that we can deploy into a single node, when it comes to Java, it feels like we're a bit of wasting space and allocation of resources, which ultimately translates into spending money that I shouldn't have to be spending, right? So, and this is really where Quarkus comes in, right? Quarkus is the so-called Supersonic Subatomic Java. And what this really means is that we can think about it as, let's say, cloud native or Kubernetes native Java. Though it is true you can still build monolithic applications with it, but it's really thought out for this cloud native world that we're living, where I have an orchestrator, where I say to that orchestrator, okay, I want to have 5 replicas of this service running. So, and it's the orchestrator's job to essentially make sure that those 5 pods are running. If one of it has some catastrophic failure and crashes, then the orchestrator will bring another one up automatically. So it's really thought out for this world. It's also really well suited for both microservices and also the so-called serverless world, the functions as a service, as is, for instance, Knative, right? Where you have functions that will execute seldomly and that should execute fast and boot up fast, right? So these are really the differentiators for Quarkus versus, let's say, the standard JVM. Okay, it's built for containers first. Okay, what this means is that you have your applications that can be built in the traditional way with a JDK, or you can really leverage the growl VM, which we'll talk about in a few slides forward. So it really gives you that fast boot time and that really low heap size in terms of making sure that your applications start fast, right? One of the other differentiators versus the vast majority of the other, let's say, frameworks for Java is that it's really tailored for the speed of development so that developers can be productive. It's one of those cases where you have live coding and live reloading for Java, which seemed unthinkable just a few years ago. But you can still take advantage of all the different libraries that you're already accustomed to. There's really not a lot of different things in terms of changes to adopting Quarkus, you pretty much get to keep all the technical knowledge that you already have in your applications. Another advantage for Quarkus is that it kind of combines into let's say a single layer both the blocking and the non-blocking world. So the blocking calls and the asynchronous calls with a built-in event bus, and really there's a lot of extensions that are already built into Quarkus. Now, Quarkus knows how to work with most of the libraries that you are already using this day. I'm thinking about Spring Boot, but there's also Hibernate, Rest Easy, integrations with stuff like Apache Kafka. I mean, there's a whole world of integrations that are already built into Quarkus, and so that you can just start making use of it, right? So you might be asking, how does exactly Quarkus become so fast, and how fast is it compared to, let's say, the legacy stacks? Well, we have here a benchmark from one of the presentations from Red Hat. You can see that, let's say, the traditional cloud native stack will take around 10 seconds to start. Quarkus plus the JVM via OpenJDK, really you can use OpenJDK or any other Java engine here. So Quarkus and the JVM takes about 2 seconds, while Quarkus native through the growl VM, it's really just a few milliseconds really. Now, in terms of memory, there's also a huge benefit to adopting Quarkus, right? While the traditional cloud native stack will take around 200 megabytes, Quarkus plus JVM will come down to roughly half the size. And if we really go for the growl VM, then we get huge benefits in terms of the memory size allocation. And so these really comes to shine when you think about the problematic that we talked about before, the density of the deployments on the nodes, and how that also affects my budget and my outcome, and also the speed to get stuff in deployment, right? How easy is it to really make it all work, right? So once we adopt the Quarkus and the JVM or the Quarkus native, really we're almost comparing ourselves to stuff like Node.js or Go, where the footprint is really small, so it gives us that density. Okay. Now, if you want to go into a bit more in depth on how Quarkus works, we have to ask ourselves, how does exactly a framework start, okay? So a framework, what it'll usually do is that you have your build time, and during this time you'll have Maven running. It'll include all the libraries, it'll do whatever it needs to package that application. And then once the application gets into this runtime phase, that's really when it loads the config file and parses the XML. It'll do all the class path scanning. It'll try to enable or disable features according to the specs. And then it'll build its model of the world. And finally, it'll start the management pool, right? So in order to achieve a fast startup time and a really small footprint, Quarkus does things a little bit different, okay? What Quarkus does is that during the build time, it'll do all of the packaging and the class map loading and all of the dependency injection that really needs to be done. And then during runtime, it'll simply just automatically start your application in almost immediate fashion, right? Right, so I mean, the brilliance of the growl VM, it's in Quarkus, it's really here. It's that all the extensions layers that you would need are already built in, right? If you are doing Spring Boot, you can just adopt Quarkus. If you are doing Netty or Rest Easy, I mean, there's a whole bunch of different Java frameworks that can start to be used alongside with Quarkus. Right, and it's really the Quarkus's core that will do all of that job, and then you can either run it in a just-in-time fashion with the OpenJDK and a hotspot, or you can go ahead with ahead of time compilation through the growl VM. Okay, what the growl VM will do is essentially it's that layer that has all the knowledge about the different frameworks that you could be including and trying to compile, and it'll translate and transform that into the growl VM compiler and native format, right? So essentially what you get is that you have your compilation phase, then it's essentially during the augmenting phase that the Quarkus core will take all those different annotations from Spring or from the other frameworks, and at that point in time you can then really choose to run it with a JDK or go ahead with growl VM and ahead of time compilation. You might be asking when to choose one over the other, and I mean there's multiple answers to this, but the simplest and fastest one is that if you have a huge heap size and you're starting a lot of stuff in during the runtime of your application, maybe you want to go with the JDK, but really if your application is lightweight, you might want to go with ahead of time compilation and the growl VM, really. Okay, so what this means is that once we adopt Quarkus, we're now tailored to start using it in microservices and serverless architectures, and it'll really take just a few dozens of megabytes of RAM to start the application and a few milliseconds to start. You replace the application layers with Vertex and Entity, which is really what powers Quarkus, and then the JVM really becomes an optional, right? So you have really fast applications that start really fast with a really low footprint, right? Now let's divert our attention to the other subject at matter, which is Istio, the service mesh, and how does it fit into really all of this platform, okay? So we were talking about the application layer. Now let's talk a bit more about the infrastructure layer, okay? So on a service mesh, what you essentially have is that you have your Kubernetes pod and your app container. And let's say that that app container is a Quarkus one. So really fast to start and really fast boot up times, right? Now your application usually has a few functionalities. Let's say an API server. So that API server needs to be secured. You might have an API client. Well, if you do, then you probably need to implement retry logic. You might have monitoring and instrumentation, let's say Prometheus, and a whole other bunch of functionalities like load balancer, circuit breaking, authentication and authorization. I mean, there's really a huge stack of, let's say, additional layers to the business logic that you have to build into your applications. Now, when you're using the service mesh, what we want to say is this, that move those responsibilities into a sidecar, okay? And the sidecar is essentially a secondary container that takes care of all those layers for you, so that your application can keep lean and really focused on the business logic, right? So it takes this logic governing the service-to-service communications and abstracts that to a layer of infrastructure that essentially uses an array of proxies. That's really what Istio is, right? When we look at this from a 10,000 foot perspective, essentially what you get is that you kind of have this web of different proxies that connect to one another and talk to one another just to form this mesh. And so this is really why you want to use Istio, right? You want to delegate the responsibility of traffic management, of security, of observability, move all of those into a separate layer that does it well and does it all once. It's based on standards. And so that eventually saves effort to your developers, it saves time, it saves you money. And also there's another concern, which is once you start using microservices, you're not limited to a single technology or a single language, right? You can choose from a multitude of different programming languages. So once you delegate those responsibilities to, say, Istio, that logic, it's always the same regardless of the language that you're coding in building your platform in. Essentially, the way that Istio does this is that you get two planes. One that it's called the data plane, and that data plane is essentially comprised of an envoy sidecar. That envoy sidecar, essentially what it does is that it's responsible for stuff like load balancing, TLS termination, HTTP2 and gRPC proxies, circuit breakers, health checks. I mean, there's a whole bunch of functionality built into that. And not only that, Istio uses an extended version of Envoy, right? And then you also get the control plane, which is let's say the layer that really deploys and makes sure that once you update some configuration, that configuration is propagated through the different proxies, that the certificates are propagated to the different proxies. You know, so for instance, Pilot, let's say, abstracts, let's say, platform specific the service discovery mechanisms. And what I mean by this is that it'll take knowledge about the different layers, and it'll take responsibility of discovering what's surrounding your cluster that needs to be updated and that needs to get a way to communicate with, right? So this is really how Istio deploys it. You get this control plane that automatically configures your data plane. So even for your developers, there's not a lot of work to be done there other than the initial configuration. Now, the thing is that deployments these days, or making sure that we have resilient platforms, a lot of times means that we're not just running one cluster or two clusters on a single region. I mean, there's always multiple cluster deployments for different regions, for redundancy, for high availability. There's a bunch of different reasons why you would want to make some considerations once you adopt Istio, okay? And some of them are, should I use Istio and make my clusters act as a single or as multiple clusters? Should they share the same network? Should they be configured as different networks? Should I use just a single control plane or spread it out? I mean, there's all of these combinations are possible. Let's take a look at some of these examples. For instance, speaking of clusters, on the left side, what you have is the so-called single cluster management. Granted, it's not as an interesting case as the multi-cluster one, where you have a single control plane and then it's managing 2 to 3 clusters in different regions. And so Istio can perfectly do that well and manage all those clusters as one and bring them all together to make things a little bit more easier to manage. You also get the ability to configure it as, let's say, a single network. Either that single network is spread across clusters and regions and subnets, or as multiple networks that are independent from one another. And I mean, there's other reasons why you would choose, let's say, multiple networks. You would get functionality stuff like, for instance, like fault tolerance, like scaling of network addresses, overlapping IPs or VIPs if it really comes down to it, okay? So you would have different networks with different gateways, all controlled by its own control plane, right? In terms of, let's say, trust models here too, you can say you can have a single mesh. Again, doesn't really matter if that mesh is spread across different clusters or into a single one. You can have a trust that works specifically for that mesh, where your proxies will use mutual TLS to authenticate with one another, or if it really comes down to it, you can also have different meshes with different certificate authorities and still manage the security and the secure communications between these different meshes. Again, doesn't really matter if these different meshes are on the same cluster or spread across different clusters, right? And also and perhaps more interestingly, and the most difficult choice to do is whether or not you want to have a single control plane or if you want to have multiple control planes. And again, you can have a single control plane that works for a single cluster, or you can have a single control plane that looks and manages different clusters in different regions. You could also have, if it really comes down to it, a control plane that it's completely independent from your service clusters, or let's say to manage different regions, you could have, let's say, a control plane per each region, and each control plane could manage different clusters. And really the advantage that you're taking in this case is that in case of a failure, the secondary control plane, even if it's on a different cluster and on a different region, it can essentially take the control of the mesh and act as the control plane for the mesh that for some reason had some failure, right? Now, it can be difficult to manage this, so you really should look into using the Istio operator, right? The Istio operator, what it'll do is that you'll get access to a set of custom resources that you can deploy to Kubernetes, and the Istio operator will essentially look at those resources, do the updates that it needs to do on the configurations and on the sidecars. It'll try to reconcile the states and the versions for the different components like Pilot and Citadel. And then once the control plane is updated, those changes will also be propagated into the data plane and into the different control proxies. Okay, so this is kind of a flash talk. We saw how we can speed up our application development and then how we can secure it with the help of Istio and delegating all of the functions for security and for metrics and other functionalities into Istio, and rely on the resiliency provided by Kubernetes and other platforms like it to really have a platform that is resilient, that is fast, and that it doesn't really take a lot of work to manage while it's being super secure. If you do have any questions, please do get in touch. There's my email. If you would like to know more about Istio and Quarkus, do get in touch with marketing@syone.com, and let's hope you keep safe, and talk to you soon. Thank you.